You might be able to guess the question that we're beginning with this week. It's very similar to the one we asked last week. That is, how are you hearing my voice right now? So, right now, you might be able to answer that I am speaking into a microphone that is going into a computer that will then be sent over the learning management system, Moodle, that you then downloaded on your computer and is playing out of your speaker. And then that goes into your ear and some magic happens and sends maybe some signals to your brain and you hear it. So hopefully at the end of the next 30 minutes, you can answer that question with a little bit more complexity and clarity. So, as you might be able to tell, this week we're talking about sound and hearing. So, we're going to start with the same question that we asked about light. What is sound anyway? Sound has some similarities to light and it also has some differences. So, sound is a vibration that travels as an acoustic wave through a transmission medium. And so we're going to talk about several different kinds of mediums. It can travel through the air. It can travel through a some kind of liquid. It can travel through some kind of solid. And it travels at different speeds throughout each of those. It is just a wave. It is not like light, because if you remember, light is both a particle and a wave. You have a photon and a wave that is emitted and registered as light. So you're dealing with your electromagnetic waves that are going up and down and side to side out from that photon. When we're talking about sound, we're only talking about a wave. So you can have complex waves that are all on top of one another, but it is just a wave. And so if we think about the kinds of things that travel as sound, we have things that you can definitely hear, like radios or maracas, some things that you can definitely hear and don't necessarily want to hear because they're so loud, like planes. And then you have things that you might not be able to hear, but we still know are sound, things like bats. So just like the wave property of light, we are going to look at the wave properties of sound. So if you remember, we talked about the height from the x-axis to the top of a wave as the amplitude. And in sound, we talk about amplitude as the intensity. So how loud something is. So if I start talking like this, you might still be able to hear me, but the amplitude is lower than if I start talking like this. So hopefully that didn't hurt your ears, but it gave you some recognition. We can also talk about frequency. And so we can talk about wavelength, but we really tend to talk about sound in the unit of frequency. And so frequency, as we talked about, is the wavelength over time. And so this is a wavelength. Frequency is how many wavelengths we have in a particular amount of time. And so frequency relates to pitch. And so if I start talking down here, this is a lower pitch than if I start talking up here. So hopefully you can tell the difference. We're going to hopefully mess around a little bit with the tone generator that will help us figure this out a little bit more. Sound also has a direction since it's a wave. So you are going to be able to hear me better because the vibrations coming from my vocal cords um, into this microphone are closer to the microphone here. So you're able to hear it better than if I'm over here when I've taken the microphone away from my mouth. So um, it has a direction, it goes in a particular way. The further away you are from that particular sound wave, the less able you are going to be able to hear it. So 3 different things that we're talking about, and we're going to talk about a 4th as well, which is speed. But right now we're talking about the amplitude, which is the intensity or how loud it is, and that is measured in decibels. The frequency, which is the pitch, so how high or low a sound is, which is related to the wavelength. It's an inverse of the wavelength, and a direction. Because it's a wave, it has to move from somewhere to somewhere else. And its strength is related to where you are in relationship to that wave. So the speed of sound is not like the speed of light. The speed of light is a constant. So no matter where you are, the speed of light is the same. And so the speed of light can be traveling through space. It can be traveling through our atmosphere. It can be traveling through water. It travels at the same speed. It is a constant. However, the speed of sound is dependent upon the medium that it's traveling through. So the speed of sound is faster in solids than in liquids or gases. And the reason that is it's faster in molecules and materials where molecules are close together. And solids, by definition, their molecules are quite close together. So if you're thinking about an aluminum can, if you beat on that, it's going to more quickly permeate that sound wave. And the reason that is because those molecules or atoms of aluminum are really, really close together in a solid. But when you think about air, for instance, so you've got your oxygen and nitrogen molecules that are sometimes bonded together, sometimes just in atoms, and they're floating through nothingness and they're not necessarily touching one another. And so since sound requires going through a medium and bouncing through something, it is going to bounce faster when there is something to bounce through. So you could think about this maybe as if you're underwater and your friend yells at you, you're going to hear that like very quickly. Versus if you're on land and a friend yells at you. So those are hard a little bit to figure out. We can think about this also in the context of something like sonar, which is where sounds are sent underwater between submarines, and this was used in World War II, for instance, to communicate messages really quickly. And so we can also think about the temperature of the medium. So at higher temperatures, then molecules are moving faster. And so, as we might expect, when the molecules are moving faster, you're more likely to run into a molecule. So, the warmer a particular um, material is, the faster you're going to move. So, you are going to hear a sound more quickly in hot air than you are in cold air. Um, and hot water and cold water and so on, because the molecules are moving more quickly, and those particular sound waves that are moving in a particular direction are more likely to hit something. They're more likely to hit a molecule than when they're not. Um, so we talked about these and it's hard to talk about sound without talking about music, and so we're going to think about this as waves propagating on a string, and what might affect a wave. So things like string tension, so how tightly a string is wound, the thickness of a string and its length affect frequency. So affect how high or low a pitch is. And so we're going to use this as a little bit of a tool to then think about um, the basilar membrane a little bit later. So when there is less tension, and I encourage you really to get a piece of string and try these out for yourself to observe them. So the less tension there is on a string, the lower the frequency is, so the lower the note is. The thicker it is, the lower the frequency. And the longer the string is, the lower the frequency. So the lowest note that you can possibly make combining these different forms is if you have a really loose string that's a very thick and a very long, will have a really, really low note, a really low frequency. If you're going the other way, the highest note or the highest frequency that we can make out of these is if you had a really, really short string that was really thin and had very, very high tension. We may not even be able to hear that vibration. So, just something to think about, and something that you can observe on your own. So we talk about notes as these singular waves, but they're actually much more complex in real life. And so this is an oboe note, and so this is an oboe. And this was just the images that were easy to find online and kind of easy to track. So if we're talking about waves the way that we've been talking about them, we would just think like that it would trace like this, right? So just up and down and up and down. But really they're much more complex because you have multiple waves that are on top of each other. And so a pure note is actually really hard to come by. And they're not very pleasing to the ear. And so we in music tend to like more complex notes that have these really complicated waveforms. And so these are two ways to think about an oboe. We're not going to go back much into the complexity of that, but important. So I don't think that I can actually make this work online, but we are going to very quickly go to a tone generator. Um, And you can play around with this. So you can increase the frequency and hear how the pitch changes, or you can decrease the frequency and hear how the pitch changes. I think it's really interesting to try to go as low as you can while you still can hear, and as high as you can and still can hear. You can also increase or decrease the volume, so increase or decrease the intensity. So be careful, you don't want to hurt. You can also change the waveforms. So these are just normal waveforms, but as we said, they are not particularly pretty. But you can also look at squares or triangles or sawtooths. So all these different types of waveforms, they don't all move in these nice sine waves, and they all sound a little bit different. So I think this is a fun um, tool to play with. I think one other thing that might be interesting is that on average, people who are younger have a wider range of hearing. And so it might be fun to try this out with your parents or maybe your older siblings, and see how high you can still hear something while they can't. Or maybe your younger siblings, and see if they can hear higher than you can hear. So if we were all in class together, we would um, explore this together, but I think it might work better online if you just do it on your own. So the second half of the lecture, we're going to talk about how the ear works. And the ear doesn't only help us hear, it also helps us maintain equilibrium. So we're going to be discussing that as well. So stay tuned.